Hello! Are you facing a research problem involving small time series data and looking for a method that helps to detect a meaningful difference, for example, before and after a training session or intervention? Well, in this video, I discussed this question using a non-overlap method that I introduced in a previous video on this channel, the Bayesian percentage of all non-overlapping data, or BANT-B. My name is Jimmy Lepping. I am a psychologist and statistician with an interest in a wide range of research topics, including psychology, education, behavioral change, research methods, and statistics. And in the next few minutes, I discuss questions such as the length of a time series needed to have a reasonable probability of detecting a meaningful effect or difference, and how the length of a time series depends on the magnitude of that effect or difference when using this non-overlap method. Now, without having to repeat an extensive explanation of BANT-B and what it is, which is an explanation that you can find in the video referred to on this screen, I'm going to start with a very brief example of a case in which BANT-B can be useful. Suppose a client is undergoing a training aimed at improving job interview skills with the idea that the training helps to improve communication skills that increase the likelihood of being the successful candidate in a job interview. Suppose we have a rubric that helps to assess these communication skills on an ordinal scale of 1, poor, 2, satisfactory, and 3, great, and the candidate undergoes a total of 8 mock interviews, 4 of which take place before training, while the remaining 4 mock interviews take place after training. Note that this design is not about causal inference in the sense that any difference in outcomes after training relative to before training is supposed to be due to the training and only to the training, regardless of whether the difference, if any, is due to the training or possibly other things, or a combination of training and other things. We are simply interested in the question whether this candidate demonstrates higher ratings on the rubric after the training compared to before the training. The people who provide the training are not involved in the assessment of the mock videos. This is done by another person who sees the 8 mock interviews in a random order without any knowledge of which mock interviews date from after the training and which ones are from before the training. So in this example, the candidate has 1 lowest or poor rating and 3 satisfactory ratings prior to the training, whereas after the training we see 1 satisfactory rating and 3 great ratings, top ratings. So BANT-B in this case counts the minimum number of points that cause overlap between the 2 periods, which is here the dot in red, and that number of points, here 1, counts as failure. Now, if this point wasn't there, then there would be 100% non-overlap, perfect non-overlap. So all the other data, which is here 7, the 7 blue dots, count as successes. Next, the Bayesian element, which is the B in BANT-B, is that the prior distribution of 1 success and 1 failure is added to obtain a posterior distribution. And the resulting posterior distribution is a distribution with a median of 0.82 and a 95% credible interval ranging from 0.518 to 0.972. If the 95% credible interval includes 0.5 or 50%, the interpretation is that 0.5, or no difference between periods, is part of the set of relatively plausible null hypotheses and hence that set of null hypotheses which we do not reject. In this case, however, the interval entirely exceeds 0.5, which indicates sufficient evidence to conclude an improvement in skills after training relative to before the training, again leaving in the middle whether this is due to the training, to other things, or a combination thereof. But how powerful is a design with 2 equal length series of 4 observations each? Well, this depends on the size of effect we are dealing with. If at population or universe level there is so little overlap between the two periods that the expected non-overlap is 0.95, there is a 94.3% chance that we will find a 95% credible interval that exceeds 0.5, because there are two possible outcomes that yield such an interval. Either 7 successes, meaning 1 failure, which we have here, or 8 successes. Now, in this chart here, the upper red line indicates the statistical power or probability of obtaining a 95% credible interval excluding 0.5 if at population or universe level there is so little overlap between the two periods that the expected non-overlap is 0.95, or hence a 5% of overlap. The horizontal axis in this chart indicates the total number of observations. So at the vertical dashed line on the left, we see 8, which is what we have in our example, 4 per period, and hence 8 observations in total. You see that for such a pronounced difference, even a limited total of 8 observations can result in a statistical power well over 90%. However, when the difference you are looking for is less pronounced, the statistical power is considerably lower. For example, to achieve a statistical power of at least 80%, you need 14 observations, 2 halves of 7, assuming an overlap of 15 instead of 5% in the population or universe. And you need 30 observations, 2 halves of 15, assuming an overlap of 25 instead of 15%. Now, with a total of 14 observations, one can have up to 3 failures in order to get a 95% credible interval above 0.5. And the probability of getting at most 3 failures, or in other words, at least 11 successes with 14 observations, is just over 85%. If at population or universe level there is only 15% of overlap. Next, in a sample of 30 observations, one can have at most 9 failures, or in other words, one needs at least 21 successes in order to see a 95% credible interval above 0.5, which has a probability of just over 80% in case at population or universe level there is 25% of overlap. And at a lower level, if the difference of interest is even less pronounced, one needs a larger sample in order to have a reasonable probability of detecting it in a sample. For example, if in a sample of 60 observations, here one needs at least 38 successes to achieve a 95% credible interval that exceeds 0.5. And if at population level or universe level there is 35% overlap, there is only about 66% chance of getting at least 38 successes in a sample of 60 observations. So to summarize, while a sample of 8 observations may be sufficient to have a good probability of detecting a large difference, it is not a good solution if the difference of interest is notably less pronounced. For the latter, larger samples are needed. Now, since usually one has no idea a priori of what magnitude or difference, magnitude of difference we are dealing with, one can consider sample size requirements under different assumptions regarding the difference of interest. And if in a given setting, such as, for example, ordinal assessments of interview skills, the researchers in charge agree that any kind of difference resulting in at most 25% overlap at population level is of interest, you can see here that a sample of 24 observations results in a statistical power of just over 76%. Finally, although In my other video, in which I introduce Band B, I explain how one can roughly compare Band and Band B with correlations. It is important to note that within-person differences can be of quite a different magnitude, and for successful interventions usually are more pronounced than between-person differences. This is important to note because despite its limitations, Band B is not always less powerful than parametric alternatives. Here, for example, I refer to a dataset first introduced in an open access book for small sample size solutions, and I reanalyzed this last year, published it in an open access journal with different statistical solutions. And one of the outcomes of that reanalysis is that for this dataset, Band B indicates a difference between conditions, whereas a linear moving average model does not. For that dataset that I just mentioned, we find 12 successes in a sample of 14 observations, which results in a 95% credible interval ranging from 0.595 to 0.957. That said, no statistical method provides a solution to all problems, and it is usually recommendable to study the same phenomenon of interest and using and comparing different statistical methods. Okay, that's it for this video. I hope you find this useful, and if you have any ideas or suggestions for future videos, feel free to leave a comment below this video or contact me via the email address shared in the description below this video. Thank you for listening and see you soon.